some results here on a PC. I get maybe about 2 million per second. On this card, we're getting about 125 million, and in the fast mode, it's about 375 million. And that'll probably, well, this will probably vary depending on your PC. And with this one, if you have a bigger FPGA or smaller FPGA, it'll vary a little bit. But there's some stats on how long it takes. So it's quite a bit faster. I'll do a quick demo here. Let's see. There we go. So let's do. All these are A3Z, so I'm just doing the fast one so you can see it work really quickly. So this is, I think, 1,000 hashes that it's cracking in parallel right now. Or, well, not entirely in parallel, but it's already found like 76 of the 1,500 hashes. And you can kind of see that how Landman works is it actually splits up your up to 14-character passphrase into two halves. And so this cracks each half independently. So this one, it's only found the last half. But with these small ones, it finds them pretty quickly. But yeah, this one, it found the half there. And so it's doing it quite a bit faster. If you think of like actually how many compares it's doing, it's about 6.4 billion compares per second. Those are all 64-bit compares. And I guess, wait, the 50, that's the wrong number, but it's probably even more than that. I don't know. So that's that. You guys have any questions about the Landman cracking stuff? Anyway, okay. So I'll close that. Now, this new thing that I threw together, Bluetooth pin cracking. A lot of people here use Bluetooth. Yeah, of course, hackers. So first off, this attack does require really expensive hardware to do. You need to have a protocol analyzer that I think costs about $10,000. So you can either try and hack your own together or buy one, but it's a little expensive to do. Basically, how this works is you use the protocol analyzer to capture the authentication, just like you do with WPA. And then you just try a pin. If all the values match up, then that's the right pin. If they don't, then it's the wrong one. And it just goes through and does all those. This attack was originally explained by, I won't even try to pronounce those names. But I guess the Thierry Zoller, is he here? Anybody? No? Okay, well, he's giving a talk tomorrow on Bluetooth pin cracking and Bluetooth hacks and stuff. And so he supposedly demonstrated this at hack.lu. And this is basically the same sort of thing that he did, but with FPGA acceleration. And all this is based off of Safer Plus. So if you capture the whole authentication for two Bluetooth devices, basically the master first sends across this 256-bit random number, and then the master also kind of generates its own random link key and runs it through an algorithm, and then sends across like an encrypted version of that. And then basically all this is kind of like a key negotiation. So after this section, both sides have the same link key, so they can actually encrypt data and send it across. After they have this link key, then they send across a random number, and this one will send across a random number. Then the other side just encrypts it with what it thinks the link key is, sends back a hash, and if that matches, then it sends back across its own random number, and the other one verifies that it has the right link key. So this is just creating the link key, and this is verifying that both sides have the right one. And so that's how the authentication works. And after the authentication, both sides know that both sides have the right pin, and they also have link keys so they can do all of their Bluetooth communication encrypted from that point on. And both sides will actually keep those link keys stored on the device, and so you don't have to keep on repairing. Like when you connect your cell phone to your laptop, you only really type in the pin once, and then it kind of remembers the pairing after that. So if you can capture this authentication, then it's a pretty small key space for just 4 digits, and so that's pretty fast in general. On a PC, I think that people have been able to do it in about 1/4 of a second, and for like 6 to 8 digits, it'll take a little bit longer, but still it's pretty quick because it's such a small key space. My implementation is a command line app that does kind of the same thing as Thierry Zoller's. And it required implementing this E21, E22, and E1 algorithms. And it actually only has one implementation of Safer. That's a 16-stage pipeline. And each one of these algorithms uses Safer in some way, and all sequentially. And so it actually runs Safer plus about 7 times, I believe. And this is basically what it does. It runs this E22 algorithm to generate kind of like an initial key. And then, well, this is how you crack it. So then you get one of these values that's actually sent across the network. And these are encrypted by XORing them with this K in it. And so you decrypt those, run them through E21, which kind of generates the link key for both sides. And then when you XOR those two together, you get the actual link key for the whole conversation. And then down here for generating these hashes to verify that the authentication is correct, then you just run these with the link key, with the random number that's sent across, and with the MAC address of the device that's sending it. And then basically if those hashes match up, then that's the right pin. If they don't, then it's the wrong one. So it just goes through every pin and tries every one until they match up. So, oh yeah, and all these red values here are values that we actually capture off the air, and this is what we're cracking. So you need to have all these different values in order to actually, crack the pin. And it's just the pin that's unknown in this whole thing. So how this whole implementation works is I have a pin generator that just generates, like pins starting from 0 all the way up to, like a 16-digit pin. And it generates the first 16 and starts sending them to Safer on each clock cycle. And because this is all pipelined, it'll take 16 clock cycles for it to fill the pipeline and actually get data coming out the other end. So you send in the first pin, and then 16 clock cycles later, you'll get the output for that pin, and then the next clock cycle, you get the output for the next pin, and so on. And so after 16 clock cycles, it actually takes the output of that and kills this whole thing here, and feeds the output back into Safer Plus because it needs to do the next E21. And so, after the 16 clock cycles, when we get the first output, it loops it back in for the input and runs the next Safer on the data. And then it basically keeps on doing this, so then it runs it through E1 by doing the same loopback thing, and the next E1, and all that. But basically, it only needs one Safer Plus in order to do the whole thing, but it loops it through 7 times in order for it to actually crack, or do 16 different pins. So after it's gone through and looped all of that, and it's gone through the last E1, then the first output value that comes out of that gets compared with the SRES values that we have. And if those match up, then it stops the whole thing and says, okay, we found the right, the right pin here, so pull it back, verify that it's right, and report it to the user. If it doesn't find anything, then the pin generator just keeps on going and filling it up again, and the whole process repeats for the next 16 pins that it generates. And all this is going at about like 100 million per second, like 100 megahertz. So if you think of how many pins it can do per second, it's basically about, like 100 million divided by 7, because it has to run it through 7 times. So, yeah, one thing that's kind of cool is that because it stops it whenever it finds the correct pin, then all we have to do is read back what the last pin was that it generated, and then subtract 16 from it, and then you know what pin actually caused it to stop. And so it kind of, that's another logic optimization there. But some results on a P4 using BT pin crack or BT crack, you're able to get about 40,000 pins per second. And with my FPGA implementation, on the low end, you're getting about 10 million per second. And if you run it at 100 megahertz, then that's like more like what, maybe 13 or 14 million per second. So pretty quick compared to that. It's about 250 times faster. And I'll show you it working right now. So let's see here. I've got these capture files that you can look at if you want. This is from one of the protocol analyzers. It's just a dump. So yeah, there's the in-rand value that it transfers across. Oh yeah, there's the COM keys. So this one is coming from the master, I think. And then, oh yeah, it's retransmitting it a bunch of times. Yeah, for some reason it does that. And then, oh yeah, there's the authentication RAND values and so on. So if you can capture these and you just take these values and then you have everything that you need. At the very end of this, you'll see the SRAND values. Where is that? ERAND. Oh yeah, SRES. There we go. Yeah, I don't know if you can see that, but there's like the 4 bytes up there for SRES and 4 bytes down there for SRES. And so those are actual hashes that we verify with. So I've got some scripts here to do this. But basically, you just run BT pin crack. You tell it to use import feature, and then tell it to import the values from that file, and then you give it the MAC addresses of the two sides that are doing the communication. So I'll just run this script here. So right now it's running on my PC, and this is a 6-digit pin, I think, that's cracking. So going at about 40,000 per second. I should find it pretty soon, I think. Yeah, there we go. So I just found it. It took, what was that, about 17 plus 1, 18 seconds for the whole thing. And after I got this to work, I tried running this on the FPGA, and it cracks this one so fast that I decided, hey, I'll just run on all the capture files, because then I can actually measure how fast it runs. So this is cracking 6 different capture files. Notice how fast it cracks the first one. Oh, oops. I gotta swap. There we go. Yeah, so just cracked the first one, instantaneous. It's working on the second one, which is like 7 or 8 digits, I think. Is that 8 digits? That's 6 one. Yeah, there. So it just cracked 6 different pins, ranging from like 5 digits to 8 or 9 digits. And it did it in maybe about 5 seconds right there. So yeah, that one was 9 digits right there, or 8 digits, yeah. So yeah, pretty cool. So the surprise release is that my friend Jake Applebaum and Ralph were doing a talk tomorrow on FileVault, and I was talking to them last night, and it turns out that FileVault actually uses PBKDF2, the same function that WPA uses for the hashing. And so it turned out that I could do some small modifications to my WPA stuff and make it work for FileVault. So I threw that together last night and actually got it working about an hour ago. And so I'm going to be demoing it tomorrow, unless you guys want to see a demo today. I can demo it right now if you want. Yeah? Okay. All right, just for information's sake, oops. The talk tomorrow is in Sol 1 at 11:30 a.m. So if you can get up that early, you should check it out. I'm not going to explain how this works too much, just, but I'll demo this also after they explain it. So let's see here. I'll just swap over to it right now. So I modified their code to do passphrase cracking, and you just feed a dictionary file and the DMG file for FileVault. So I've got this dict file. It's the same one for the WPA stuff, kind of same sort of stuff. So feed a dictionary file and the DMG, which is test.dmg there. And so it's running through with PBKDF2 on it. It runs about 4 times faster because it only does 1,000.